Well, here is the another session of unit number 2, which is bipolar junction transistor and its biasing. In this session, I am going to cover a couple of topics like the first one here is base width modulation, which is also known as early effect. Then remaining characteristic for common base configuration. Thereafter, I'm going to explain common emitter configuration of transistor, where again we will define the current gain, but this current gain would be of common emitter configuration, and we will derive the mathematical expression for all the currents: collector current IC, emitter current IE, and the base current IB. And for this common emitter configuration, I will explain the input, output, and the transfer characteristic. After that, common collector configuration of transistor. We'll see how to bias the transistor when the common collector configuration of the transistor is done. Then current gain for common collector configuration, and again all the current components like collector current, emitter current, and the base current for common collector configuration, and each of the characteristic for CC. After that, interesting topic would be relation among current gains alpha, beta, and gamma. Thereafter, we will derive the relation between the leakage current ICBO and ICEO. And at last, we will do the comparison of all these three configurations, which is common base, common emitter, and common collector. And at last, we'll try to solve one example based on certain derivation we will do in this session. So let us begin with the first topic, that is base width modulation. Uh, the statement for the base width modulation, which is also known as the early effect, is the change in the effective base width due to change in VCB is called the base width modulation or the early effect. What is VCB? VCB is the voltage applied between collector and the base terminal when transistor is connected in the common base configuration. Right. So earlier we saw that when we want to operate transistor in the active region, the emitter base junction should be in the forward bias condition and the base collector junction should be in the reverse bias condition. And to make the base collector junction in the reverse bias, we connect VCB supply between the base terminal and the collector terminal. And due to reverse bias condition, the depletion region is created at the junction base collector. So in CB configuration of transistor, if we increase VCB, that means we are trying to reverse bias these base and collector more and more. So because of that, the width of the depletion region increases, right? Here you can see that width of the depletion region is this much, but as we increase VCB, the width of the depletion region increases. Because of that, what happens to the width of the base region? Here you can see that width of the base region is very less when VCB is increased. But with the lower value of the VCB, the effective base width is large, right? It means that if we keep on increase VCB, the effective base width reduces. What happens because of this? Because of this, concentration gradient at the emitter base junction will increase, which allows more electrons from emitter to diffuse into the base, right? Because of that, more and more electron will cross the emitter base junction and move towards the base region, and hence emitter current will increase. Thus, when the collector base voltage VCB increases, emitter current will also increases, right? So the effective base width is dependent on VCB. If we decrease VCB, the width of the base region increases, and if we increase the VCB, width of the base region decreases. So this phenomena is known as the base width modulation. It is also referred as early effect. Base width modulation means changing the width of the base region. Moving ahead, let us discuss the output characteristic of the common base configuration. What is output characteristic? First of all, output characteristic is the characteristic between output current IC and the output voltage VCB, right? It shows the relation between two output parameters. Voltage is on the x-axis and the current is on the y-axis. For a specific magnitude of emitter current, here emitter current is the input current. So for specific magnitude of emitter current, the relation between IC and VCB could be discussed. So here you can see that when the VCB is negative and it tries to reach to the zero value, the magnitude of the collector current rapidly increases, right? But once the VCB becomes positive, then increment in the IC is very slow compared to increment in IC when the VCB was negative. So here you can see that when we increase VCB by a larger magnitude, but IC increases by a small margin. So you can see that here the curve is almost flat, right? So the first curve that is corresponding to emitter current is 0. Second curve is for emitter is equal to 1 milliampere. Then emitter current is equal to 2 milliampere and so on. So this characteristic also shows that when the emitter current increases, then collector current also increases. Even in the previous session, we also saw that collector current is approximately equal to emitter current. So obviously, if emitter current increases, IC must increase, right? Even all the three regions are shown in the characteristic. The first region is the saturation region, which is mentioned over here. Second region, which is active region, that is shown here. And the third region, which is the cutoff region, it is shown over here, right? So here you can see that the cutoff region is corresponding to the region which is the area below IC is equal to ICBO curve, that is this one. This region is known as cutoff region, right? When the magnitude of the collector current is very less, and ICBO is nothing but a leakage current. So in the past, we understood that the magnitude of the leakage current is negligible, is almost zero. So the area under this curve, this line is known as cutoff region. Right? So this is the output characteristic. of common base configuration. What is this breakdown region in the output characteristic that I'm going to explain? Breakdown region, which is shown over here. Let me highlight that region. This is the breakdown region, right? So you can see that uh, for this region, the magnitude of VCB should be much higher, right? For example, here the range is given starting from the 0 volt. Here it's a 5 volt, 10 volt, 90 volt, and so on. So for the breakdown region, the voltage applied between the collector and base terminal must be too much high. What is this breakdown region? Let us discuss about this. So in the next slide, which uh, gives us the key point about the output characteristic, right? The output characteristic, as I said, is the relation between the transistor output current IC and the output voltage VCB while keeping the input current constant, right? That is I emitter current is equal to 0 milliampere. That is case number 1. Then for the case number 2, when the emitter current is kept constant at 1 milliampere and draw the characteristic between IC and VCB, we get the second curve. Similarly, keep the IE at 5 milliampere constant and draw the characteristic between IC and VCB, we get another curve, and so on. So if an excessive reverse bias voltage is applied, that means if we increase the VCB beyond certain permissible value, then the device breakdown may occur. And what is the reason behind this device breakdown? As the reverse bias voltage VCB increases, the collector base depletion region also increases, right? So in base width modulation, we saw that as VCB increases, the effective base width decreases. Why? Because the width of the depletion region increases. So if an excessive reverse bias voltage is applied, then this collector base depletion region penetrates into the base. Penetrates into the base, that means this depletion region widens more and more into the base region until it makes contact with the emitter base depletion region. That is the first junction, emitter base. The junction between the emitter and base is the first junction, and the junction between the base and the collector is the second junction. So the depletion region of the second junction makes contact with the first depletion region, first junction's depletion region. This condition is known as the punch through or the reach through effect, right? When these two junctions, when these two depletion regions are touched to each other, that condition is known as the punch through effect, or it is known as the reach through effect. That means the second depletion region reaches at the first depletion region, and because of that a very large current flows through the transistor, and sometimes it may damage the device. So the breakdown region, which is shown in the output characteristic, that is not the good sign for the transistor. We should ensure that magnitude of this VCB should not go beyond certain values so that we can avoid this breakdown region. We can avoid this punch through effect in order to prevent the transistor, right? Let us discuss the transfer characteristic of common base configuration. Transfer characteristic is nothing but the relation which shows the relation between the output current and the input current. So for the common base configuration, the output current is collector current and input current is the emitter current. And from earlier discussion, we understood that as emitter current increases, the collector current obviously increases. So the relation between these collector and emitter is in the direct proportion, right? So here you can see that as emitter current increases on the x-axis, the collector current is also increases on the y-axis. So here the relationship between the collector and the emitter current is the linear one. And if we talk about the slope of this characteristic slope of this curve, then what is the slope? Slope of this line is nothing but the delta y divided by delta x. You might have studied this in mathematics subject, that when we want to find out the slope of any line, then we do y2 minus y1 divided by x2 minus x1. So this is nothing but the delta IC, that is y2 minus y1, that is change in the y-axis parameter, and delta IE, that is change in the x-axis parameter. So it is the ratio of change in the output current and change in the emitter current. But what is the output current divided by input current for the common base configuration? That is the current gain, right? So it is also termed as alpha AC. Moving ahead, the next topic is the common emitter configuration. In the common emitter configuration, you can see that emitter terminal is common between the input base terminal and the output collector terminal. Here the RB and RC are the current limiting resistor for the base and the collector terminal respectively, right? And the voltage between collector and emitter terminal is VCE, and the voltage between base and emitter terminal is VBE. So this is how we can have the common emitter configuration in the transistor. So current gain for this configuration, current gain is nothing but the output current divided by input current. So here output terminal is the collector terminal and input terminal is the base terminal. So obviously the current gain for common emitter configuration is defined as output current IC and input current IB. But the notation used for current gain in this common emitter configuration is beta, right? So here you can see that IC is nothing but the IC minus ICEO, where ICEO is the reverse leakage current between collector and emitter terminal, that is between these two terminals when the base terminal is kept open. That means when we do not apply this VBB supply to the transistor, at that time due to the minority carrier flow occurs between this collector and emitter junction, and that results into ICEO, that is known as the reverse leakage current between collector and emitter region when base terminal is open. But as we understood that the magnitude of this leakage current is uh, always very small, so sometimes we can neglect ICEO or such type of leakage current for simplification in the derivation, right? So if we neglect ICEO in this equation, then the current gain for the common emitter configuration is defined as uh, beta DC is equal to IC divided by IB. IC is the output current for this configuration and IB is the input current for this configuration. Moving ahead, collector current. Let us derive the relation for each of the current. The first one is the collector current. So collector current is IC is equal to beta DC into IB plus ICEO. So this equation is derived from this previous slide, right? Here I am making IC as a subject of equation. So when I send this IB on the left hand side, it gets multiplied with this beta DC. So IC on the right hand side, and when I send this ICEO on the left hand side, it becomes positive. So IC is equal to IB into beta DC plus ICEO. So that is the collector current, right? And uh, we can neglect ICEO for the simplification purpose, and because of that the equation for the collector current becomes IC is approximately equal to beta DC into IB, right? Let us derive the let us derive the equation for emitter current, right? As we know that emitter current is nothing but it is the summation of collector current and the base current. But what is collector current for this common base configuration? Collector current is equal to beta DC into IB. So substitute this beta DC into IB into this equation. So we get IE is equal to beta DC into IB plus ICO, and then that ICEO. That means, sorry, this equation is substituted over here, right? Actually, the upper equation, the first equation is substituted into the emitter equation. So this one, and this IB is from the equation. So we get IE is equal to beta DC IB plus ICEO plus IB. So on the right hand side, we have two terms which has IB. The first term is this one and the second term is this one. So we can take IB as common from these two terms. So we get IB into 1 plus beta DC and ICEO as it is. But by neglecting ICEO, we can write equation for the IE. That is, IE is approximately equal to IB into 1 plus beta DC, right? So that is the emitter current when transistor is configured in common uh, emitter manner, right? Where emitter is common between base and collector. And what is base current? So base current, once we have IC and IE, then we can easily find out this IB. That is, IB is equal to IE minus IC, right? Okay. Moving ahead, input characteristic for common emitter configuration. So now by this time we know that input characteristic is the characteristic shows the relation between two input parameters. The first is the input voltage and second is the input current. Input voltage for this configuration is VBE and input current for this configuration is input current is IB. So it is shown over here IB, and input voltage is shown on the x-axis, that is VBE, right? So here we can see that once again this junction is in the forward bias condition. That means base emitter junction is in the forward bias condition, so it behaves as a forward bias condition diode. So the input characteristic is exactly looks like a forward biased diode characteristic, right? And here you see that two curves are shown in the characteristic. The first one is for VCE is equal to 5 volt, and the second curve for VCE is equal to 15 volt, right? What is VCE? VCE is the output voltage for this one, that is here the voltage the voltage between collector and the emitter terminal. So what happens if I change VCE while maintaining the input voltage at some specific value? Right? You can see that the effect of change in the output voltage on the input characteristic in the graph is over here. Input voltage is kept nearly constant at 0.75, and when VCE is equal to 5 volt, you can see that the input current is 60 microampere, right? Let us keep VBE at 0.75 as it is. That means I'm not going to change this VBE voltage. But if I increase VCE, then what happens to the base current? If I increase VCE, that means over here, VCE is equal to 15 volts. So we get this another characteristic. And because of that, uh, when we take the projection on the y-axis, you can see that emitter current is 20 microampere. So the conclusion is that when the output voltage increases, then for the same input voltage, input current reduces, right? Input current reduces, that is from 60 microampere to the 20 microampere. So that is the input characteristic of common emitter configuration. Now, this is the output characteristic of common emitter configuration. So that shows the relation between output voltage VCE and output current IC for the common emitter. So for the common emitter configuration, right? For a specific value of IE, for specific value of IB, the curves are drawn. So here you can see that first curve is for IB is equal to 0. When the base current is 0, then the relation between IC and VCE is somewhat like this. When IB increases, then IC also increases for the same value of collector emitter voltage, right? And here also you can see this breakdown region, that is due to excessive value of VCE, that is output voltage. So in common emitter configuration, this collector emitter junction is in the reverse bias condition. So if we do not keep limit on this VCE, that means if we keep on increasing VCE, uh, it may happen that depletion region which is created at this collector emitter junction reaches through the base region towards the base emitter region, depletion region of base emitter, and because of that punch through effect, the magnitude of the current increases beyond the permissible value and it may damage the transistor. So we always keep in mind that there has to be uh, there has to be limit on VCE to avoid this breakdown region in this output characteristic of common emitter, right? Then this is the transfer characteristic when the transistor is in the common emitter configuration. So transfer characteristic, as I said earlier, it shows the relation between output current and input current. So here input current is IB for the common emitter configuration and output current is IC, right? And from the mathematical derivation we understood that the relation between IB and IC is linear. So that means IC IB is proportional to IC, right? So if I increase IB, IC gets also increased. So for two different value of VCE, the relation between output and the input current is shown, right? So the transfer characteristic is the linear characteristic when the transistor is in the common emitter configuration. Moving ahead, common collector configuration. So here the diagram is shown for the common collector. you can see that collector terminal is common between input base terminal and output emitter terminal, right? So and this circuit can be redrawn like this, right, where emitter is the output terminal, base is the input terminal, and the collector is the common between this emitter and the base terminal, right? So as shown in the figure, EB junction is the forward bias. EB junction, that is over here, base emitter junction is in the forward bias due to this VBB supply, and collector base junction, that is this one, collector base junction is in the reverse bias, right? So to forward bias EB junction, VBB battery is connected, and to reverse bias this collector base junction, VCC battery is connected. And RB and this RE, these two are the current limiting resistors for input terminal base and the output terminal emitter respectively. So current gain for this configuration, here the output current is emitter current and input current is the base current. So the current gain is the ratio of output current to the input current. So here you can see that IE divided by IB, and current gain for this collector configuration is denoted by gamma DC. That DC stands for the biasing to the transistor is DC. Batteries are connected uh, between the terminals. So this expression can be written as IC plus IB in the numerator, and IB is the IB is in the denominator. Why? Because we know that IE is IC plus IB, so that is substituted in the equation. We also know from the previous discussion that IC is equal to beta DC into IB, right? So that we can substitute in the upper equation, beta DC into IB. So IB and IB is present with the both terms. So we can take it outside, and that IB gets cancelled with the denominator IB. So only 1 plus beta DC remains. So gamma DC is approximately equal to 1 plus beta DC, right? So collector current. So all three currents for common collector configuration. The first current is the collector current. Collector current is, we know that IC is equal to alpha DC IE plus ICBO. And from common emitter configuration, we know that IC is equal to beta DC IB plus ICEO, right? We know that ICEO is very small, and if we neglect ICEO, then collector current is approximately equal to beta DC into IB, right? So in this equation, if we neglect this ICEO, then IC becomes beta DC into IB. What about emitter current? So that is the with the basic equation of emitter current, which is IE is equal to IC plus IB. But what is IC? So we are substituting IC from this one into this equation, which gives us IE is equal to beta DC IB into ICEO, and IB as it is, right? IB is present in the first term as well as in the last term. So when we take IB as common, then the equation becomes IB into 1 plus beta DC and ICEO as it is. Again, if we neglect ICEO, then IE is approximately equal to IB inside the bracket 1 plus beta DC. And the base current, which can be derived from this equation by making IB as subject of equation. So IB is equal to IE minus IC. That is over here. IB is equal to IE minus IC. Moving ahead, input characteristic for common collector configuration. So which shows the relation between the input parameters for collector configuration. Here the input parameters are VDC input voltage and IB input current, right? So you can see that the two graphs are shown for so two curves are shown for this relationship. The first one is corresponding to VCE is equal to 1 volt and second is VCE is equal to 2 volt. So beyond certain value, when we increase VBC, the input current linearly increases, right? That is for 1 volt, and for 2 volt, when we increase base collector voltage beyond 2.5 volt, the base current linearly increases. So this is the input characteristic for common collector configuration. Then output characteristic, where the output voltage is VEC and output current IE, the relation between these two output parameters for different value of input current IB. For IB is equal to 0, when we want to see the relation between IE and VEC, then this graph can be drawn. And for second value of the input current, when we change output voltage, then output current changes in this manner. So here also you can see that as the base current increases, output current, emitter current is also increases, right? So moving ahead, transfer characteristic for common collector configuration. Transfer characteristic is the relation between output current and the input current. Here output current is the emitter current and input current is the base current. So you can see that for different value of output voltage VCE1, the relation between IE and IB is this graph, and for VCE2, the relation between IE and IB is this graph. What is VCE? What is the relation between VCE and VCE1 and VCE2? VCE2 is larger than VCE1. This VCE1 and VCE2, these are the voltages applied between collector and the emitter terminal, or you can say the output voltage. So you can see that transfer characteristic for common collector configuration is the linear relationship between the output current and the output emitter current and the input base current. Right, now let us derive the relation among the current gain alpha, beta and gamma. Right, so alpha, beta and gamma. So let us start with the basic equation, that is emitter current is the summation of the base current and the collector current. And let us take this equation as equation number 1. So when we divide this equation by IC collector current on the both side, so on the left hand side we have IE divided by IC, and on the right hand side we have IB by IC plus IC upon IC, right? But we know that the ratio of collector current to the emitter current is alpha, so 1 upon alpha. And we also know that the ratio of collector current to the base current is beta. So here beta is substituted, but ratio of IC to IC is equal to 1. So we have the equation number 2, right? On the right hand side, by taking beta as LCM, we can further simplify the equation number 2 as alpha is equal to beta divided by 1 plus beta, right? So here you can see that beta is taken as LCM. Then after dividing this equation by 1, we get alpha is equal to beta divided by 1 plus beta. So that shows the relation between current gain alpha and current gain beta. Current gain alpha is the current gain when the transistor is in the common base configuration, and beta is the current gain for the common emitter configuration, right? So here alpha is represented in terms of beta. We can also represent beta in terms of alpha, that is from equation number these two, by making this 1 upon beta as subject of equation. For that we have to send this 1 on the left hand side. So the equation number 2 results into this 1 upon beta is equal to 1 minus alpha minus 1, right? And simplification of this equation results into equation number 4, that is current gain beta is in terms of alpha, right? Now let us build up the relation between current gain gamma and current gain beta. So for that again, starting from the basic equation, IE is equal to IB plus IC. Now divide the equation number 5 with IB on the both sides. So on the left hand side we have IE divided by IB, on the right hand side IB divided by IB plus IC by IB. But just now discussed in the common collector configuration, the ratio of output current IB and the input current IE is the gamma, that is the current gain for common collector configuration. Then here IB divided by IB, that is equal to 1, and uh, ratio of IB to IC is nothing but the beta, that is current gain for the common emitter configuration, right? So the equation number 6 shows the relation between current gain gamma and current gain beta, right? Now the relation between the leakage current ICBO and ICEO. ICBO is the current between the collector base terminal when the emitter terminal is open, and this is the current between collector emitter terminal when the base terminal is open. So again, starting with the basic equation, emitter current is IB plus IC. In common base configuration, uh, we wrote down the IC, that is collector current, is equal to alpha IE plus ICBO, right? So here in this equation, we substitute IE is equal to IB plus IC. So the equation number 1 results into this one, IC is equal to alpha times IC plus IB plus ICBO, right? On the right hand side, when we open the bracket and multiply this alpha to IC and IB, the first term will be alpha into IC, and when this first term is sent on the left hand side, IC is present, and the term which is sent on the left hand side has also IC, and when this IC is taken common, then on the left hand side we have 1 minus alpha into IC, and on the right hand side alpha IB plus ICBO as it is. So by making by making IC as subject of equation, that means I am sending this 1 minus alpha in the denominator of the right hand side. The equation becomes IC is equal to alpha divided by 1 minus alpha into IB plus 1 upon 1 minus alpha into ICBO, right? With this one, we can further uh, go for the derivation. But in equation 2, what is the equation 2? It is shown in this slide, that is over here. In the equation to this alpha divided by 1 minus alpha is nothing but it is equal to beta, and 1 minus alpha is nothing but 1 divided by 1 minus beta, right? From equation of the alpha, you can do the derivation and you can get 1 minus alpha is equal to 1 divided by 1 minus beta, right? So these two things are substituted into equation number 2. That is, first one is this beta. So here we have beta into this equation, and 1 minus alpha is nothing but the 1 divided by 1 plus beta. So when this is substituted into this equation, we get this one plus beta into ICBO. But in common emitter configuration, the collector current is given by IC is equal to beta DC IB plus ICEO, right? So what I'm going to do is I'm going to compare equation number 3 and equation number 4, right? Both have IC. So when we compare these two equation number 3 and equation number 4, then we get the relation between ICEO and ICBO, right? Because you can see that when I substitute, okay, let's do that. When I substitute equation number 4 into equation number 3, that means I have to place this beta IB plus ICEO over here. So beta IB on the left hand side and beta IB on the right hand side. Get these two gets cancelled. So on the left hand side we have only ICEO, but on the right hand side we get 1 plus beta into ICBO. So this equation number 5 shows the relation between these two leakage current, the leakage current ICEO and the leakage current ICB. Now let us compare each of the configuration, that is common base, common emitter and common collector configuration. Number of the parameters are considered for this configuration. So the first parameter is the common terminal between input and output. Which terminal behaves as a common between input and output in each of the configuration. So here you can see that for the common base configuration, the base is the common between input and output terminal. In common emitter terminal is the common between input base and output collector terminal. Similarly, in common collector terminal, in common collector configuration, the collector terminal is the common. Which one is the input current for each of the configuration? In common base, input current is IE. In common emitter, input current is IB. And in common collector also, the input current is IB. Output current in common base configuration is IC. Common emitter configuration is also IC. And common collector configuration is also IE. What about the current gain? So common base configuration, the current gain is alpha. Common emitter configuration, current gain is beta. And common collector configuration, the current gain is gamma. That is the ratio of output to the input current. So in common base configuration, output current is IC because output terminal is IC, and the input current is IE because input terminal is IE. Similarly, for common emitter configuration, output terminal is collector and input terminal is base. And in common collector configuration, output terminal is emitter and the input terminal is base. What is the typical value of the current gain for each of these configuration? For common base configuration, the current gain is very less. In common emitter configuration, the current gain is comparatively high than the common base configuration. Even in the common collector configuration also, the current gain is high, right? Then input voltage, which is the input voltage for each of the configuration. So if you remember input and output terminals very well for each of the configuration, then you can easily mention an input and output voltage for common base, common emitter, and common collector configuration. What about the voltage gain, right? Voltage gain for the common base configuration is medium, and for common emitter configuration, voltage gain is the highest, and for the common collector configuration, voltage gain is low. Voltage gain is nothing but the ratio of output voltage to the input voltage, right? Input impedance. Input impedance means uh, the impedance at the input side, right? So for the common base configuration, the input impedance is very low and the typical value is 20 ohm. And for common emitter configuration, the input impedance is medium. The typical value is nearly 1 kilo ohm, and input impedance is highest in the common collector configuration, which is typically near to 1 mega ohm. Output impedance, for output impedance, common base configuration is good because it has highest output impedance, which is nearly 1 mega ohm. Then even common emitter configuration has also the high output impedance, but not as much high as common base configuration. Uh, so the typical value of output impedance for common emitter configuration is 40 kilo ohm. And for collector configuration, common collector configuration, the output impedance is very low, which is nearly 50 ohm. Right? Moving ahead, next is the next parameter for the comparison is the power gain. So here you can see that power gain in the common base is medium, common emitter configuration it is high, and the common collector configuration it is medium. What about the magnitude of leakage current in each of the configuration? So leakage current is comparatively higher in common emitter and common collector configuration compared to common base one. Signal phase, that means what is the phase displacement between input and output signal, right? So here you can see that in common base configuration, the in phase with the input, that means output signal is in phase with the input. In common emitter configuration, the output signal is out of phase with reference to the input signal, and this for the common collector configuration, the output signal has the same phase as the input signal has. Applications where can I use these common base, common emitter, and common collector configuration? So the common base configuration can be used as a pre-amplifier, that is the stage before the amplifier stage. Then common emitter configuration can be used as amplifier stage, audio amplification, and common collector configuration can be used for the impedance matching. What is impedance matching? When two or more circuits are interconnected, at that time we must ensure the impedance of one circuit should be matched to the impedance of another circuit. That means output impedance of the first circuit should match input impedance of the second circuit, so that we have the proper interconnection of the circuits without any kind of interferences propagated without any kind of interference gets propagated from one circuit to another circuit. So as of now, you may not get proper idea about impedance matching, but in uh, future you will have idea about what is impedance matching. So out of these three configuration, common emitter configuration is the most preferred configuration, right? So what are the reasons behind it? So the first reason mentioned over here is it has high current and a high voltage gain. So in the comparison table, we saw that The current gain and the voltage gain for the common emitter configuration is very high. Even power gain is also high in common emitter configuration. And apart from these two advantages, input and output impedances are moderate to high level. And because of these, common emitter configuration can be used as a coupling purpose, right? So no need to connect any impedance matching circuit while we connect one circuit to another circuit, as I said, to avoid the propagation of interference from one circuit to another circuit. Because of these advantages, common emitter configuration of this transistor is widely used in most of the application. Let us solve one example based on the derivation we did in the session. Here is the problem statement. Problem statement says that for NPN transistor connected in common emitter configuration as shown in the figure. So here the diagram is also given as a part of problem statement, but sometimes you may not be given the diagram. You have to make the diagram based on the information given in the problem statement, right? Here the information is given like common emitter configuration. So you should know the circuit diagram of common emitter configuration. Which terminal is the input one, which terminal is the output one. What should be the current limiting resistor, like in the common emitter RB and RC are the common current limiting resistor. Base terminal is the input one. So VBB as the input supply and VCC is the supply between the collector and emitter terminal, right? So all these things you should remember, right? But here the diagram is given as a part of the statement, so there is a not it's not a big deal for this example, right? So here you can see that calculate the transistor current and alpha, right? Transistor currents means emitter current, collector current, and the base current. These three currents should be calculated, and alpha. Alpha is the current gain for common emitter configuration. Alpha is nothing but the output current divided by input current. So if we are able to find out these three currents, then we can easily find out alpha, right? Because alpha is the ratio of two currents. So let us first of all find out each of the current. So how to begin with the solution? First of all, we have to note down the parameters given inside the problem statement as well as the circuit diagram. So RB is equal to 200 kilo ohm, RC is equal to 300 kilo ohm is mentioned, VBB is equal to 5 volt, and VCC is equal to 10 volt. This data is given. So by applying KVL at the input side, right? That means I am applying the KVL at the input side. At the input side means over here, that is here. So starting from the supply, the first term is VBB, then this terminal is the base terminal, so the current flow in the base terminal is IB, right? So when IB passes through this resistor RB, then the voltage drop takes place across RB is mentioned as IB into RB, and the voltage drop takes place between this base and emitter terminal is VBE. That means going from positive to negative, it should be minus VBE. So in actual, the equation would be like VBB minus IB, sorry, VBB, VBB minus IB RB minus VBE equal to 0, right? So when we make this VBB as a subject of equation, and by sending these IB, RB and VBE on the right hand side, the equation becomes like this one. VBB is equal to IBRB plus PBE, VBE. Now substitute the value from the problem statement and the circuit diagram. What is VBB? VBB is equal to 5 volt given. IB is the unknown, the current we are supposed to find out. RB is also mentioned in the circuit diagram, that is 200 kilo ohm. So do not forget to multiply this 200 by 10 raised to 3, right? And what is VBE? VBE is not mentioned either in the problem statement or in the circuit diagram. But here VBE is taken as 0.7. What is the reason behind it? The reason behind it is base emitter junction is in the forward bias condition, and this transistor is of NPN type. So base is made up of P layer and emitter is made up of N layer. So P and N type layer are combined, and forward bias is given to this PN junction. So it behaves as a forward biased diode, right? So voltage drop across the forward bias diode is approximately 0.7. So we can take VBE is equal to 0.7. So this is based on this assumption, we are calculating all the currents: base current IB, collector current IC, and emitter current IE, right? So when we substitute IB is equal to 0.7, then you can see over here that IB is equal to 21.5 microampere. So here you have to make IB a subject of equation by sending this 0.7 on the left hand side and 200 into 10 raised to 3 in the denominator of the left hand side. So you get IB is equal to 21.5 microampere. That is our first answer. Then let us find out the second current IC, collector current. We know the equation for the collector current, which is in terms of base current, right? We know the base current now. Base current is equal to we got in the previous slide as 21.5 microampere. So we can easily substitute that 21.5 microampere into this equation, right? Even in the problem statement, beta is also beta is given. And what about ICO? ICO is also mentioned in the problem statement, right? So here you can see that beta is equal to 100 and ICO is equal to 2 into 10 raised to minus 8 milliampere. These two values are mentioned. So we can easily find out IC just by substituting value of beta from the statement, IB from the previous slide, and ICO from the statement. So IC is equal to 2.15 milliampere. So this is the second current we have found out. Now moving to the third current. That is very simple. Why? Because IE is nothing but IB plus IC. We have calculated IB, we have calculated IC. Just add these two currents, we get the IE. IE is equal to 2.70 milliampere. Then we are supposed to find out the current gain. What is current gain? Current gain alpha is IC divided by IE. We calculated IC, we calculated IE. So by just substituting IC and IE into these two equations, we get alpha. This is the first way to find out alpha. And the second way to find out alpha, if you know the value of beta, right? Beta is straight away given in the problem statement as 100. So when we substitute beta is equal to 100 into this equation, we get alpha is equal to 0.99. That is 100 divided by 1 plus 100. So 0.99. Right. So that's it for this session. I hope this may help you to understand the topics behind which I have discussed. I would suggest you to go through at least once through the material which we have given to you. And if you find any difficulty, then feel free to contact me. Thank you. Thank you very much.